Good morning, take your seats. So, today we can see the solutions of the written test problems. And we start from the first problem. So we have a large disk which can rotate about point O, and it has radius r. And also there is a smaller disk which can rotate about point O prime. And this axis of rotation O prime is fixed on the large disk. So when the large disk rotates, the axis O prime also moves along its own circular trajectory. And this disk has radius r small, which is uppercase R divided by 3. And this is also the radius. And according to the statement of the problem, there is point A on the rim of the small disk at some arbitrary angle, angle phi. And the two disks rotate in different directions with the same angular velocity which is given. The question is, what is the trajectory of point A? Unfortunately, no student was able to draw correctly this trajectory. How can we solve this problem? First of all, we choose a coordinate system. A coordinate system consisting of unit vectors I, J, and K, but we don't need this z-axis because everything in this problem occurs in a plane which will be IJ plane or XY plane. So this is x-axis and this is y-axis. Everything occurs in this XY plane, so we don't need a third vector K. Okay, if all this is moving and rotating, then point O prime will somehow move in time, and at an arbitrary point in time, at an arbitrary moment of time, point O prime on this axis will be somewhere at an arbitrary place. Well, for example, we know that O prime moves along a circular trajectory, so at some point in time it will be at an arbitrary point of its trajectory. And that will be characterized by radius vector r1. And also there is a point A which is located at distance r from the axis of rotation O prime. Somewhere there is point A, and that will be radius vector r2. And this point O, the origin of coordinate system, let it coincide with the axis O of the large disk. So this point and this point is the same point. I have drawn this axis separately in order not to complicate or overcomplicate this picture. So this point O actually coincides with this axis O of rotation. I need to know the trajectory of point A, which will be described by radius vector. Well, let it be simply r. According to the rules of addition of vectors, we can write that vector r equals vector r1 plus vector r2. What is vector R1? It can be presented using its components. So it will be unit vector I and component x1 plus unit vector j component y1. Just x1 and y1 are the coordinates of vector R1. But this vector R1, according to the statement of the problem, is not fixed in time. It's moving, it's changing in time, it's rotating, So that this angle, let it be angle alpha, changes in time. It's a function of time. What function of time is that? We know that the rotation takes place at constant angular velocity, so that the angle of turning this vector is proportional to time, and the coefficient of proportionality is the angular velocity, so that this angle depends on time in such a way. And then the coordinates x1 and y1 of this vector R1 will depend on time in the following way. The length of this vector R1, that is the distance of point O prime from point R, from point O, and this distance is given. It's indicated here as small r. Well, that is not very good, because small r also is the vector OA. And OA definitely does not coincide with capital R divided by 3. So let us denote this vector. It was not a good idea to denote it by small r. Let it be simply A, vector A. That is O, vector OA. So here we have vector A, which is, I put it in such way, vector OA. So that the length of vector R1 is known. It's the distance between axis O and O prime. It's small r. And therefore, x1 changing in time because this vector is rotating. How can it change in time? It will be small r, its amplitude, cosine omega t, plus vector j, and again vector r, and its y component will be equal to sine omega t. What is vector r2? This vector is also rotating. It's also rotating. It's changing in time. All these vectors are functions of time. So vector r2 can be presented in similar way using the unit vectors I and j. And again, it will be the length of this vector r2 is the radius of the small disk, which is small r. And its coordinates can be presented as cosine, but the initial phase was phi. Initial phase, when the time was 0, initial phase was phi. And then we know that this vector rotates at angular velocity omega, but in different direction. So if here omega is positive, then here omega should be negative, because the rotation is in different direction, in opposite direction, according to the statement of the problem. Plus vector j, again the amplitude of vector r2, the length of vector r2, which is small r, sine initial phase phi minus omega t. the same argument. That's very simple. If this vector r1 rotates at constant angular velocity, then its coordinates will be cosine, which is x coordinate, and sine, which is y coordinate. And the argument is proportional to time. It changes with angular velocity omega t. And the initial phase here was 0 because the initial condition, initial position of this axis was given to you on the picture. The initial position of point O prime coincides with axis x. So that the initial angle of this vector O prime was 0, and the initial angle of vector O prime A was given as phi. So in the first line, the initial phase was 0, and nothing is added here to omega t. But the second vector O prime A has some initial phase. It was given to you. So the initial phase, why do we call it initial? Because this is the argument of cosine. This is the phase at initial time, when time is 0. Then this is 0, and we get this initial phase phi. And the same rotating angle, rotating in different directions, so that here we put minus omega, and here also minus omega. We could have chosen for positive direction something different. For example, we could have chosen this positive, then the omega in the first line would be negative, and the omega in the second line would be positive. That would change nothing. The trajectory of point A will not depend on such a choice of positive direction of rotation. We can choose positive direction of rotation either clockwise or counterclockwise. That will not influence the final trajectory of point A. It's as if you shoot a video clip about the motion of point A, and then you watch this video, you run it forward, and then you run this video backward, in backward direction. You will see the same trajectory of the motion of moving point A, but first time the point A will move in one direction, and when you run the video in opposite direction, you will see the point running in opposite direction. But the curve will be the same, the trajectory will be the same. So time reversal is possible here. It will not change the result. It will not influence the final answer, the final curve along which point A moves. The time may be reversed in this. In classical mechanics, time can be reversed. It's not always the case in quantum mechanics. In quantum physics, sometimes time cannot be reversed. If you reverse the time in quantum physics, some phenomena will go on in different way. So in quantum physics is different. But in classical physics, it's always possible to reverse the time, and everything will be okay. The picture will be in compliance with classical laws of mechanics, laws of classical mechanics, whatever direction of time arrow you choose. So we have simple representation of rotating vector r1 and rotating vector r2. This is simple representation of two vectors. And now we have, in order to find the trajectory of point A, we have to add these two vectors to find the OA vector. We have to add these two vectors. What can be factored here? I will group the first term in the first line and the first term in the second line because they have the same direction along the unit vector I. So unit vector I and amplitude R will be the common multiplier, and inside the square brackets I will get cosine omega t plus cosine phi minus omega t. And also I will group the remaining terms which are directed along the j unit vector. That will be j amplitude r, and here I will have sine omega t plus sine phi minus omega t. Some students were clever enough to obtain this formula, but they were unable to do the next step in order to determine the trajectory, to draw the trajectory. You need to simplify somehow this formula. You need to simplify it in order to draw, in order to understand what is the trajectory. You have to simplify it. And in order to simplify this expression, I will need well-known formulas for the sum of cosines, that is cosine alpha plus cosine beta is known to be 2 cosine alpha plus beta divided by 2 and cosine alpha minus beta divided by 2. And now another sum of two sine functions, sine alpha plus sine beta is known to be 2 sine alpha plus beta divided by 2 cosine alpha minus beta divided by 2. That's it, if I had not mistaken. Oh, everything's okay. So using these formulas known in from trigonometric functions, I will somehow transform this expression and obtain the following. IR remains unchanged, and the sum of two cosines will be what? 2 cosine, and I have to take the sum of these two arguments and divide it by 2. When I add omega t and minus omega t will cancel. The only argument remaining here will be phi divided by 2, according to this formula. And then I have to multiply it by cosine and the difference between these two vectors. So I will have to subtract the second argument from the first one, or the first one from the second one. That makes no difference. And when subtracting, I will obtain 2 omega t divided by 2, so it will be omega t minus phi over 2, because we divide by 2. And then plus the second term that was directed along the unit vector I, and the second term will be directed along the unit vector j with amplitude r. It will be 2 sine of the sum of these two vectors divided by 2, that will be phi over 2, and cosine of the difference, that is 2 omega 2 divided by 2, that is simply omega 2 minus phi over 2. That is, we have to use trigonometric formula in order to transform this expression, which is not easy to understand. It's not easy to imagine what type of trajectory is that. But in order to do anything about it, we will be able now to understand what is common factor. Common factor is 2r, which is seen here and here. Common factor is 2r, and also cosine here and cosine here. So I will factor this expression 2r cosine omega t minus phi divided by 2. And what remains in square brackets? vector I multiplied by cosine phi over 2, I cosine phi over 2, plus vector j by sine over phi over 2, j sine phi over 2. That's simple algebraic transformations. Now it's very easy to understand what is that all. What is in square brackets? Some vector. First of all, does it depend on time? No, this is a constant vector. What is this vector? For example, what is its length? To calculate the length, I have to take this coordinate squared plus this coordinate squared. Cosine squared plus sine squared will be unit. So this is a unit length vector. This is a unit vector which constantly looks at the angle phi over 2 with respect to x-axis. What is phi over 2? I will draw this picture again in a larger scale so that we have a triangle OA, and this is O prime, and this is R, and this is R, and this is vector phi. So in any triangle, this angle equals the sum of these two angles. And here, these two angles are equal because the triangle is isosceles, because this side equals to this side. This is an isosceles triangle, so this is angle alpha and this is angle alpha. And as phi equals 2 alpha, then alpha equals phi over 2. So this vector here, constant vector, looks along this direction towards point A, and it's constant. Let's denote this vector by anything, like vector B. That's it, constant vector B. And what is here? The amplitude of this vector. Cosine changes as time goes on. Cosine changes between +1 and -1. The maximum value of cosine is +1, and minimum value is -1. So this is coefficient which changes from 2r to -2r. How does it change? In harmonic way, just like a cosine function, so that the final amplitude is sometimes equal to 2r and sometimes to -2r. Therefore, the trajectory of point A will be a straight line going through the center, and the length of this line will be 2r here and 2r here. So the total length will be 4r. The total length of this line will be 4r, and the line will be inclined so that it will go through point A and initial position of point A at the angle phi over 2, and the trajectory of point A will be that. It will go along this line, straight line, to and fro between the two limit points. That's the trajectory of point A. It will go along the straight line at angle phi over 2, at this angle, to and fro, to and fro. Why do we know that? Because it's easy to understand what this mathematical formula means. It's a constant vector B with some varying amplitude, sometimes positive, sometimes negative. That's it. That's the solution of the first problem. Some students obtained this formula, but they were unable to take a further step, to simplify this expression in order to understand what is really the trajectory of point A. So you failed in mathematics, in trigonometry. You failed your fault was poor knowledge of trigonometric transformations. Any questions? Many students thought the trajectory would be a circle. No, certainly not. The two disks rotating in different directions, one direction omega, another minus omega. You can even visualize this process. You can imagine what may happen here, and you can visualize what could be the trajectory of point A. It will not be a circle in any way. So, any questions? Okay, let's go to other problems. If you don't know how to derive these trigonometric formulas, find the derivation and learn how to obtain these formulas. You should know such mathematics. You should know such mathematics. You will need it at any exam in physics or mathematics. You will need such formulas very often. So the second problem is a body on a plane. So how to draw it? We have a plane which is inclined at angle alpha to the horizon, through the horizontal. This is horizontal, and this is also horizontal line. And the plane is such that there is a body, and a coefficient of friction is given, and alpha is given. And it's known that we start acting with a force F on this body, and if the force is small, the body will not slip. It will remain without moving. It will remain fixed on the plane. But if the force grows at some moment, at some minimum possible force, the body will start moving naturally, yes. Sooner or later, we will be able to move the body. And the first question is, what is the value for this minimum force which is needed to move the body? And the second question, at what direction, at what angle beta the body will start its motion? So if the body starts moving here along some unknown direction, we don't know what is angle beta, but we know certainly that it will start moving at some direction. Well, probably this one. If it starts moving at some direction, then what about the force of friction? Where should the force of friction be directed? The force of friction is always directed oppositely the displacement, opposite the velocity. If the velocity of displacement is along this dashed line, then the force of friction will be directed oppositely. And what is the force of friction? It's always given as the coefficient of friction and the force of normal reaction of the surface. That's the definition of the coefficient of friction. And the normal reaction for the body which is on the inclined plane is well known from many other problems. It's mg cosine alpha, where alpha is given and m is the mass of this body. Why do we know that this is a force of normal reaction? Because this is the perpendicular component of the weight of the body, mg, perpendicular to the surface, to the inclined plane. This is the, we have considered this situation. We solved many such problems, and you know this, you should know this well, that this is the component of the weight of the body, perpendicular to the surface. And the force of friction is always found as this component, which is actually the force of normal reaction from the surface, times coefficient of friction. That will be the force of friction, and the force of friction will be directed here. Also, we know that there is a force which tends to move the body along the surface downward, and this is mg sine alpha. This force, on many occasions we considered. You should know this. This is the component of the weight of the body which is directed along the surface, parallel to the surface. And this is the component of the weight of the body directed normally to the surface, or along perpendicular line to the surface. All this is well known to you. The only thing you have to guess is that when the body starts moving, the force of friction will be directed oppositely. Opposite its displacement, whatever direction of displacement, whatever direction. We may move the body in this direction, or upward, or at some arbitrary direction. If the body moves along this line, the force of friction is opposite. That's the property of friction. So, at the very first moment, when the body starts its motion, the vector sum of these two forces, F and this one, the vector sum which can be found according to the parallelogram of vectors, this vector sum should be equal to the force of friction, because force of friction cannot be larger than this. It's always smaller or equal to this expression. And we need such force of friction which is maximum, because at this point when the force of friction is maximum, the body will start its motion. And at the moment when the body starts moving, the vector sum of F and mg sine alpha will be equal to this force F. How to use this idea, how to express it mathematically? Very simple, because this is a right triangle. Why do we know it's right? Because it's given that the force is directed along the surface and horizontally. Horizontally, it means that this force is parallel to this side. Force F is parallel to this side. And this force is perpendicular to this side. So this is the right angle. We know that the triangles involved are right triangles, both this one and this one. So that we can write, according to Pythagorean Theorem, F squared, this is not the vector, this is the magnitude of vector F, plus force of friction squared, plus this another side of the right triangle, which is mg sine alpha squared, must be equal force of friction squared, which is, force of friction is known, it's kmg cosine alpha squared. That is the Pythagorean theorem. Pythagorean theorem for this triangle. And in order to use this Pythagorean theorem, we have to understand one simple physical fact, that the sum of these two forces, which is defined by the diagonal of this parallelogram, should be equal to the force of friction to its maximum possible value at the moment when this body starts motion. At the very moment when the body starts moving, then this force is equal to this force. When the body starts moving, this force is a little bit higher, a little bit larger than this one. But practically, they are equal. when the body starts moving. That's physical condition. Physical condition that when we increase the force F from 0, at first the force of friction increases until its maximum value, and then the body starts moving. So based on this idea, we can write the Pythagorean theorem for this right triangle. And now the force of friction will be found from here as the square root kmg cosine alpha squared minus mg sine alpha squared. It can be somehow transformed, like mg squared may be factored before the square root, mg square root k squared cosine alpha squared minus sine squared alpha. So, and what is this angle beta? That is the first question in our problem. The first question was to find the minimum possible force. We have found it. That is the minimum possible force. And the second question, what is angle beta? Which defines the direction along which the body will start its motion. How to find angle beta? Well, we know, for example, the tangent of this angle can be found as the opposite leg divided by this leg. Or we can define the sine of this angle. Maybe that will be easier. The sine of beta will be the opposite leg, which is mg sine alpha, the opposite leg mg sine alpha divided by this diagonal, which is the force of friction, kmg cosine alpha. Mg will cancel, sine divided by cosine is tangent, alpha divided by k. That's it. Some students wrote this formula, but unfortunately without any explanations. Why don't you explain your actions? Why don't you explain your solutions? Very few students use words to explain what you're doing. Many just write down the formulas and believe that's enough. No, that's not enough. Actually, you must explain every formula. You must write down what law of physics is that, or what mathematical theorem is that. If you don't write it down, I believe that you don't know what is that. You don't understand your own solution if you don't use the words to explain it. That's the only conclusion. So, 5 minutes interval. So we continue with problem 3. A homogeneous rectangular plate. A homogeneous rectangular plate standing near the wall in the corner starts falling without the initial velocity. It starts moving. So it falls and then hits the floor and continues sliding along the floor without friction. So finally it will go with some velocity, which we must find. It will slide without friction. Why? Why will it slide? Because if this point was fixed by some axle of rotation, then it will fall down and hit the floor and it will not slide if this point was fixed here. But this end of the plate is not fixed. It means that when it starts falling, the center of mass will have some horizontal component of its velocity, And this horizontal component at first grows and grows and grows, and then the horizontal component must diminish somehow. But due to what force will it diminish? When the horizontal component grows as the plate falls down, we understand that there is a force of gravity pulling the plate down, and also the force of reaction from the vertical wall, which actually ensures that the center of mass velocity has some horizontal component. But why should this horizontal component diminish down to zero if the plate hits the floor? There is no force to retard the plate, no force to diminish the horizontal component of the center of mass. No force, because forces of friction are absent here. Therefore, the plate will start falling, and then it will fall with acceleration, and then at some point it will lose contact with the wall and go along such trajectory that it will move from the wall, and this horizontal component of the center of mass will remain constant because there are no horizontal forces acting on the falling plate, because no forces can act on it from the wall as this end of the plate has separated from the wall, no contact with the wall. Then, after hitting the floor, the plate will continue sliding without friction at constant velocity, which is the maximum horizontal velocity. I'm not sure if it's maximum or not. We will find this horizontal velocity, maybe not maximum. Oh, it should be maximum, certainly, yes, I understand it. It should be maximum. So, because it cannot diminish. So, also it's important to understand that when the plate hits the floor, this impact is absolutely inelastic. If it was elastic, then the plate would hit the floor and jump up, and then again hit and jump. Nothing like that happens here. So when the plate hits the floor, this is absolutely inelastic impact. And we know that mechanical energy is not conserved when you have inelastic impact of some bodies, some objects. Any inelastic interaction implies the loss of some mechanical energy. So those of you who attempted to use the law of conservation of energy were absolutely wrong. This is wrong to use the conservation of energy here, because energy is not conserved because the impact is inelastic. And so that the final kinetic energy of this plate sliding along the floor will not be equal to the initial potential energy, because the center of mass is at some height, mgh. Potential energy will be lost, but not all the potential energy will be transformed into final kinetic energy. Some potential energy, some initial mechanical energy will be lost when the plate hits the floor. So, we know that this center of mass moves along some circular trajectory here, but it does not move to the end. The motion of the center of mass with some velocity of the center of mass, which is a function of time or a function of this angle, angle alpha. This is the function of angle alpha. The motion of the center of mass is described and governed by well-known law of physics, the law of motion of the center of mass. What is this law? It looks like the second Newton's law. Total mass of the body times acceleration of the center of mass equals total force. Total forces, net force acting on the body. That is the vector sum of all forces acting on the body. What forces act on this plate? First of all, mg, the weight of the body, which is applied to the center of mass and pulls it downward. And secondly, there is some force of reaction in this point. We know very little about this force about the force which acts on the plate from the floor and from the wall. But there is some force, surely, We know that. If there were no force here, for example, if there were no wall, then and no friction, then the center of mass would just slip down and the plate would go this way, and the center of mass would go down vertically if there were no forces acting on this end of the plate. So there are some forces acting both in horizontal and vertical directions, but we don't know what is the direction of this force. Anyway, whatever direction of this force is, we can always decompose this force into two perpendicular directions. The first one will be parallel to the plate, and the second one will be perpendicular to the plate. So the force of reaction here, I will denote it by N. I don't know what is the direction, but it will have some parallel component and some perpendicular component, and whatever the sum of this component, I don't know, but there should be some components. We can decompose any vector along two perpendicular directions, any directions which are convenient for our solution. And in this particular case, two directions are convenient. One is is parallel to the plate, and another is perpendicular to the plate. And so if we consider this equation for the motion of the center of mass, we consider the component of these vectors along the plate, that is the parallel component. That will be what? The parallel along this plate, the acceleration will be the acceleration of the center of mass will be directed towards the center, and that will be the centripetal acceleration. And we know what is the centripetal acceleration. That is the velocity of the center of mass squared divided by this distance, by the radius of this circle. And the radius of the circle is just half the length of the plate. And the length of the plate, I don't know let it be L, the vertical length of the plate. So it will be divided by L over 2, half the length. That is the radius of this circle, the circular trajectory along which the center of mass of the plate moves. So that is the mass times centripetal acceleration, and that should be equal to the total force acting in this direction, parallel to the plate. What is the component of the weight of the plate along this direction? So if this angle is alpha, then this angle is also alpha, and I will need this component, which will be mg cosine alpha. Mg cosine alpha, that is the component of mg of the weight along the plate, in direction parallel to the plate. And also there will be opposite force, which is n, which is opposite, which is n parallel. Y minus sign, because n parallel we know is directed here, and mg cosine alpha is directed here. Opposite directions. Mg cosine here, downward, and the force of reaction from this corner along the plate is directed oppositely. So these two forces have absolute opposite direction. And the centripetal acceleration will be directed here to the center O in the same direction as the component of vector mg, so that these two components will have the same sign, positive sign. They are directed in the same way. What happens if this first term is larger than this first term? Then the right-hand side part of this, the right part of this equation will be positive, and the centripetal acceleration will be positive, and the body will move in such a way that its center of mass has centripetal acceleration. That is, the center of mass will move along this circular trajectory. But what happens if what happens if n equals 0? What happens if n equals 0 and parallel? what happens in this moment? In this moment, no horizontal component of the force will act in this direction, and the plate will lose contact with the wall. It will lose contact with the wall. It means that it will cease going along the circular trajectory, and it will start going at some other trajectory other than circular. So it will lose contact with the wall when this force is 0. At this particular moment, the contact will be lost, and at this particular moment, the horizontal component of the velocity of the center of mass will become constant, because from this particular moment, no horizontal forces will act on the plate, only vertical components of forces. At the moment when these forces equal 0, then from this moment on, the horizontal component of the velocity of the center of mass will remain constant, because no forces will act in horizontal component. And that is the moment we need to catch. We need to analyze this particular moment, because we will need to find this horizontal component of this velocity, because that will be the final velocity, v. That will be the final velocity. So that velocity, v squared, velocity of the center of mass, at this particular point, when n parallel equals 0, we can find it here. M will cancel, and it will be Lg cosine alpha divided by 2. That's the velocity squared of the center of mass at the moment when the plate loses its contact with the vertical wall and no horizontal forces act here anymore. That's the very important moment. And we know what's the connection between the velocity of the center of mass, total velocity, and angle alpha at this particular moment. Do we know anything else about this velocity? Yes. We know that when the plate was going down, when it was falling, the mechanical energy is conserved. Before the plate hits the floor, the mechanical energy is conserved. There is one force acting on the plate, which is the force of gravity, but this is a potential force. It has its potential, and we know that the potential energy will be diminished here, will be decreased, and part of potential energy will go into kinetic energy of rotating plate while it's moving, while it has not yet fallen on the floor. So the total mechanical energy is conserved. Certainly there is some force applied to the plate here, but this force, the point of application of this force here, of force N, this point of application does not move. So this force does not perform any work. It performs no work, because work is force times displacement. And this point does not displace until the plate is separated from the vertical wall. I mean, this end of the plate is separated. Until this separation happens, this force performs no work, because the displacement of this end of the plate is 0. But after this separation, there will be no work performed, because there will be some displacement of this end, but there will be no forces acting on it. So anyway, the work performed by these forces is 0. And we need to take into account only the work performed by the weight of the plate as the center of mass goes down, and we have to use this conservation of energy during the falling of the plate. I repeat that no conservation of energy applies after the plate, applies when the plate hits the floor. This is the loss of mechanical energy. But before the plate has hit the floor, before this, while the plate is falling, while the plate is moving and turning, the conservation of energy is applicable, and we can use it. So mgh, the loss of potential energy and this is the potential. H is the loss of potential energy of the center of mass, will be equal to the increase of kinetic energy, which is I omega squared over 2. What is I? I is the moment of inertia about the point, the fixed point about which the plate rotates, about this point O. So this is the moment of inertia about axis O. It's very strange what I found in your papers, in your works. You considered this plate falling down, and somehow most of students took into account the moment of inertia about the axis which goes through the center of the plate perpendicular to the plate. Most of the students used this formula, that is m a squared plus b squared over 12. This is the moment of inertia about the axis which goes through the center of the plate and the axis directed perpendicular to the plate. Does the plate rotate about this axis? No. In this problem, the plate rotates about this axis in such a way. Who told you to use this formula? I don't know. I don't know who ever told you, but most of students used this absolutely wrong formula. This is inapplicable. Yes, this can be applied in different problems. This is correct if the axis of rotation is perpendicular to the plate and goes through its center of mass. But in our case, it's not perpendicular to the plate. It goes through its end, and it's parallel to one of its ends. So in our particular case, this is absolutely incorrect. I don't know who advised you, most of you, to use this formula. So in our case, the moment of inertia should be calculated as that of the uniform rod of length L, ml squared over 3, rotating about one of its ends. Not about the center of mass, but about one of its ends, this end. So that's the moment of inertia. And omega, the angular velocity, can be certainly can be related to the velocity of the center of mass. The velocity of the center of mass will be angular velocity omega times this radius, and radius is L over 2. L is the length, the vertical length of the plate. So omega is easily related to the velocity that will be divided by L multiplied by 2. Using these formulas, we can transform the energy conservation law, the L energy balance, in a simple way, which we have performed many times. That will be mg. What is h? H is calculated as this radius, which is L over 2, minus the same radius L over 2 cosine alpha. So that will be radius L over 2, 1 minus cosine alpha. That is the h, the loss of height of the center of mass. That is mgh. And now we have to write down this 1 over 2, moment of inertia ml squared over 3, and omega squared will be 4 divided by L squared, velocity of the center of mass squared. L squared will cancel, and the velocity of the center of mass squared can be expressed from here. Mass will cancel, and what will remain here, GL divided by 2, and this 1 over 2 will cancel. So what we will have, the coefficient will be 3 divided by 4. M cancels, GL, 3 divided by 4, that's it. Oh, 1 minus cosine alpha, certainly, in round brackets. So this is the relationship between the center of mass velocity and angle alpha. This relationship is obtained from the law of conservation of energy, which holds while the plate is falling until it falls, until it hits the ground. This velocity, this conservation law should be applicable. No, I must be more precise. We take into account only rotational motion here. We take into account only rotational motion. So this formula of conservation of energy holds only when the plate falls down while touching the wall. After the plate lost its contact with the wall, it will acquire some additional translational motion of its center of mass along with rotational motion. So at some moment of time we will have to add here some additional term related to translational motion energy. But until the plate has not touched its contact with the vertical wall, until the very last moment this conservation of energy holds. Until the very last moment of when the plate loses its contact with the vertical wall. So this formula holds until this very last moment. This is the relationship between the velocity of the center of mass and the angle of the plate. And also we know the relationship between the velocity and the angle at the very last moment when there is a contact between the plate and the vertical wall. So at this moment the contact is lost because this formula was obtained on condition that this force is zero. So we have two formulas which apply to one and the same moment in time. So that this expression can be equated to this equation. LG will cancel and we will obtain 2 cosine alpha. I multiply by 4 immediately. I multiply by 4. I obtain 2 cosine alpha equal to 3, 1 minus cosine alpha. And that's the condition for the angle alpha at which the contact between the vertical wall and the plate, falling plate, will be lost. At this particular angle, the contact will be lost. So that 5 cosine alpha will equal 3, and cosine alpha will equal 3 over 5. That's the angle at which the contact here will be lost. And we know that at this particular moment in time, the velocity of the center of mass will have some horizontal component which will remain constant on after this moment. The horizontal component, which is velocity v. And velocity v is the horizontal component of vc, the velocity of center of mass. And the horizontal component can be found in which way? If this is alpha, then the horizontal component, then this is also alpha, and the horizontal component will be vc cosine alpha. And that's the final answer, actually. We need to find this horizontal component. We know that it will be conserved because the floor is ideally smooth and there is no coefficient of friction. So this no horizontal forces. So this horizontal component will be conserved due to Newton's second law. How can a velocity be changed? Only if there is a force. But according to the statement of the problem, there are no forces acting on the plate from the floor because the floor is ideally smooth. The plate is sliding without friction. So this is the horizontal component of the center of mass velocity, and that will be the final answer to our problem. I need just to calculate it. Is it difficult to calculate it? No. I know the VC at the last moment, that one. That will be Lg divided by 2 cosine alpha, but I know what is cosine alpha is 3 over 5 at this particular moment. 3 divided by 5, that is the cosine alpha. So this velocity will be 3 over 10 Lg. The final velocity with which the plate will slide without friction along the floor. That final velocity is the horizontal component of the velocity of the center of mass at the moment when the plate lost its contact with the vertical wall. Because starting from this moment, there will be no forces acting in horizontal direction. And that velocity will remain constant. Is that clear? The question? Sorry? What? Oh, sorry. Yes, just a moment. VC. Yes, we have to take a square root. Yes, so sure, yes. So VC will be, this is not VC squared, this is VC. And I have taken this expression, which is VC squared. So that must be a square root, this one. Yes, here. And cosine will be 3 over 5. So this is not correct. So it will be something like 3 over 5 square root Lg divided by 2, something like that, right? Yeah, probably so. Any questions? Sorry? Sorry, 3 over 5 is cosine. Sorry, I don't hear you. Can you come here and show me? Come here, please. If you know, yes, come here, please, and show. What's the matter? The sound here is echoing. It's difficult to understand you. Yeah. Yes, you're right. Absolutely. So 3 over 5. And another cosine. Yes, another 3 over 5 is here. Yes, absolutely, you are correct. So I'm in a hurry, and that's why it's better to write everything logically and not miss the intermediate transformations. So that is the VC, and that will be a square root of Lg. Cosine is 3 over 5, and 2 here, 3 over 10 under the square root. So that will be the VC, and we must multiply it by cosine. So the final velocity will be here, like VC, that is, and the cosine 3 over 5, and the square root of 3Lg over 10. Yes, that's correct. Yes, you're right. Absolutely so. So, any more questions? Yes. So, I will not discuss problem number 4 because practically all the students understood that third Kepler's law must be used here. And the problem is very simple. because you need just to, in this problem, you need just to use the third Kepler's law without any transformation. The simplest problem, the simplest. Just take the formula and substitute the data, and you understand that the period of rotation of a planet or a satellite and another period for another planet, another satellite squared is the same as the major semi-axis for the first planet or satellite and major semi-axis of the orbit of the second, and that is in cube. So the third Kepler's law, and in this problem 3 parameters are given, 1, 2, 3 are given. Just substitute figures in this formula and obtain the unknown parameter. Practically everyone has done it, so I will not lose my time on this simple problem. And we will consider the last problem here. The last one. So there is a rod of mass m and length L, and point A, the upper point of this rod, and some small ball of mass m over 2 flies with velocity v and strikes the lower end of this rod, and the rod is on the horizontal surface, lies on the horizontal surface of the table, so it's just look from upward, from above on the surface of the table, and the table is smooth and the rod can slide without friction on the surface. And after this impact, the rod will move somehow, and the motion will depend on the character of this collision, and it's indicated that the collision is totally inelastic, absolutely inelastic, so that this small ball sticks to the rod and will be here with its mass m over 2. And the rod's center of mass is here, but after, at point O, after the small ball has stuck to this rod, the center of mass will be here. And many of you have found that the center of mass will be displaced at some section L over 6, so that this is L over 3. Many of you have found it. The center of mass of the new body is very simple to find. The mass of the rod is concentrated in its center of mass, in the center, and here at the end is another mass m over 2, so the new center of mass will be here, at the distance L over 3 from this end, and at the distance 2 L divided by 3 from another end. This is very simple, but what next? We have to find the displacement of point A after the rod with the small ball stuck in it has made a complete turn of 360 degrees. So we don't know the trajectory of this point. It may be something like that. The trajectory may be something like that. But finally, when the rod will make the total complete turn, the point A will come here, and we need to find the displacement. The displacement, this distance, let it be d. So what is this distance? What do we need to calculate this distance? First of all, we need to know the velocity of the center of mass, because center of mass will be displaced here to its new position. We need to know the velocity of the center of mass of the system, and we need to know the period of rotation, so velocity times period, and the period of rotation may be calculated as 2 pi angular velocity of the rotation of this system. How to find the velocity of the center of mass? So there are two things we need to find, the center of mass velocity and the angular velocity of rotation. How to find the center of mass velocity? We must use the law of conservation of momentum. We must use the law of conservation of momentum, which means that the initial momentum, which is m/2, and initial velocity will equal the total momentum of the system after the collision, after the inelastic collision. And the total momentum will be total mass m plus m/2 times the velocity of the center of mass. Law of conservation of momentum. Initial velocity of the system, initial momentum, should equal to final momentum. Why? Because there are no external forces acting on the system. No external forces. Only internal forces of interaction. Under these conditions, the linear momentum is conserved. For a complicated system, we must take the total mass and the center of mass velocity. So from here, we easily find the center of mass velocity and substitute it here. I will not waste my time. How to find the remaining parameter here, omega? We must use the law of conservation of angular momentum. Angular momentum, initial angular momentum with respect to the final center of mass. That will be the momentum times the aiming parameter L/3. That is the distance from the line along which this body moves to the center of mass. And that will equal the final angular momentum. Final angular momentum will be the total momentum of inertia of the system. That is the rod plus the mass which is stuck here. And this angular momentum should be calculated with respect to the point C, with respect to the axis which is perpendicular to the rod and which goes through point C. And omega, that will be the final angular momentum of the system. The initial angular momentum, only the moving ball or the moving puck makes its impact, makes its contribution into the initial angular momentum. But final angular momentum will consist of all the bodies moving here. So how can we calculate the total moment of inertia? That will be the moment of inertia of the rod, ml squared divided by 12. That is the moment of inertia with respect to point A, plus, according to Huygens-Steiner theorem, m distance x squared, x is just L/6, and plus the angular momentum of the small ball, whose mass is m/2 times the distance from the center of mass, which is L/3 squared. And this is L/6 squared. So the total angular momentum will be what? M can be factored, L squared can be factored, and here we will have 1/12 plus 1/36 plus 1/9. Oh, another 2, so that will be 18. The common denominator here will be 36, and you will have to multiply this term by 2 and this term by 3. So 2 plus 3, 5, and 1, 6. 6 divided by 36. So that will be ml squared divided by 6. And that will be the total moment of inertia. And if you know the total moment of inertia, you can easily calculate omega from here and then substitute omega into this formula and find the displacement. If I am not mistaken, the correct formula will be 2 pi over 3L. If I'm not mistaken, yes, that's correct. I remember. That's the correct answer. So we have considered the solution of all the problems. The problems were based on the knowledge which you must have, which we have discussed. All the laws of physics we have discussed, we derived and obtained all the laws. You must know them, and you must be able to apply these laws in solving different problems. And so this written test was a kind of repetition before the exam. In the exam, you will have a written exam with practically similar problems. I mean, similar in the level of complexity. That's it. Okay, thank you. That will be the end of our lecture.